Can you hear me? Yes, you can. Okay. So first of all, let me thank the organizer who gave me the opportunity to present the physics at Jefferson Lab. I'm going to show you, first of all, the scientific mission of the lab, the transition between the 6 and the 12 GeV upgrade, and then I pin down a couple of examples of the physics that has been done extensively at 6 GeV, the nuclear elastic form factors. I will talk about the meson spectroscopy that represents, in some sense, part of the future of the facility at 12 GeV, and then I will give you an example of, let's say, unconventional nuclear physics experiment running at Jefferson Lab. That is another kind of physics that, due to the very good performance of the machine, has been pursued for the future, and also, I mean, with some experiment in the past. So, scientific mission of Jefferson Lab: understanding how hadrons are constructed from quarks and gluons of QCD. The idea is that you can try to understand the transition between the region that you can describe in terms of nucleon and meson to the correct degree of freedom of QCD that are quarks and gluons. Then, obviously, as an extension of this program, the idea is to try also to interpret the nucleon forces based on QCD Lagrangian, that so far as very only limited phenomenology can describe it directly from first principles. You really need to have some effective theories or some, let's say, phenomenological models. So obviously a nuclear structure needs to be investigated with high precision, short distances experiment, and obviously the question that we are trying to address and to try to respond are related to what's the mechanism of confinement of quark within the nucleons, for instance, and the dynamics of quark-quark that makes the strong interaction as strong as it is and different from any other interaction that we know. And then in the very last years, there was also another, let's say, path related, as I mentioned before, related to high precision test of the standard model and experiment beyond the standard model. That in some sense is possible to run experiment close to what people at high energy colliders like LHC are doing. So Jefferson Lab is an electron machine located in Newport News, Virginia. It's a couple of hour ride from Washington, D.C., so it's quite convenient in terms of logistic. The energy beam has run up to 6 GeV in the past. Now it's going to be upgraded to 12 GeV in a very short time. Actually, the commissioning of the beam at 12 GeV is already started. And if you look at the wavelength corresponding to this energy, you can explore the region between 10 to 0.1 Fermi. That is exactly the transition region between the degree of freedom of QCD, let's say quark and gluons, and meson and nucleon bound states. Obviously, another important part of the 6 GeV program was about the baryon and meson excited states that is going to be also will run also in the 12 GeV era, but it was mainly for the 6 GeV, since this is the kinematics that is reachable with 6 GeV is better suited for this kind of search. One of the characteristics of the beam is that it is almost a continuous beam. It means that you have an electron beam that bunches are separated by 2 nanoseconds. So from the point of view of the detector of what you are getting, the final states that you are measuring, the beam is almost continuous. And the advantage of that is that if you are running an experiment with many particles in the final state and you want to avoid the pile-up, due to the optimal way is to have a continuous beam. You don't have the charge all accumulated in a single bunch and then you wait for a while. You have the particle coming and you have time to detect the final states of your product. So this is a very important technology. I think it was one of the first CW beam available. Now it's kind of technique that is used by many other accelerators. But when CBAF, that is the Continuous Electron Beam Facility Accelerator, born, I mean, a long time ago, this was really a new feature and very important feature. And another important point is that polarization degree of freedom are available with both in terms of the electron beam that is always polarized since you have high energy electrons, and from the point of view also of reaction products. There are polarimeters and other instrumentation or polarized target that allows you to run experiment with both electron and I mean double or even triple polarization experiment. Just to give you an idea, the luminosity we're talking about for CBAF is about 1 million times higher than what was for the classical DIS experiment running as LAC in the 70s and the 80s. So you can imagine that in 1 day of measurements you get almost 1 million more particles and the final states as it was collected by the original experiment in this field. And with the 12 GeV, there will be another factor of 10 increase in luminosity. So the machine is quite simple. You have almost 2 LINACs here. You inject electron at very low energy, and then they pass through radio frequency cavities that accelerate electrons. And the particles, you make one pass, they got, for instance, 400 MeV, each electron. Then they are recirculated on this arc that just bend the electron trajectory, go through the other LINAC section, getting another 400 MeV. So at the end of one pass, you get 800 MeV. Then you can decide if you want to send the beam directly to the holes, the experimental hole here, or if you can have the electron passing again for another 800 MeV, for instance, pass, and at the end you can pick up the electron after a certain number of passes. So depending on that, you can have the energy between, let's say, a few hundred MeV, or let's say 500, 600 MeV, that was the minimum energy that we ran in the past, up to 6 GeV. Originally, you see here 400 MeV. Actually, the design of the machine was so good that we were able to operate routinely at 6 GeV. So the capability of the machine was increased by 50% very easily. So again, this is an aerial view of the site. You see the 2 LINACs, the arc, and the 3 end stations, all A, B, and C. Polarized electron source that produce the electron that are injected in the LINAC area with radio frequency cavity, and the arc where the electron beam is bent. And then the 3 holes are instrumented with different kind of instrumentation. Hole A has 2 big head in the past, 2 high-resolution spectrometers. So it is a typical, let's say, nuclear physics experiment where you detect, for instance, the scattered electron and, for instance, the proton for the elastic scattering of to measure the form factors, for instance. And you have the momentum range goes up to a few GeV, so you can imagine these are very huge magnet that almost full and a huge hole that is the hole A at Jefferson Lab. With the high luminosity, obviously the solid angle that you can cover with such a spectrometer is very small, so the product of the luminosity by the acceptance, by the solid angle covered, allows you to extract a cross-section also for rare processes. And then there are polarimeters, for instance, implementing the focal plane of the spectrometer to measure polarization of particles produced. And then there were also some dedicated detectors that for specific installation for specific experiment that ran during the years, like for instance calorimeter for the DVCS. DVCS is the deeply virtual Compton scattering that required to measure a photon going forward in a dedicated calorimeter, or big bite spectrometer that came from NICEF, or neutron detectors, for instance. ULB hosts a 4-pi. This is a typical 4-pi high, let's say, high energy detector based on a toroidal magnetic field. So it's like Atlas, just to give you an idea. And the advantage of a toroidal magnetic field is that it's obviously very ununiform. So you have a strong field in the front part of the front part and the weak field in the back part. And this makes sense because in a fixed target experiment, you all the reaction products are boosted by the Lorentz booster, and so they have a lot of energy going forward. So you need to bend them and to analyze them magnetically. You need to have a strong field in the forward direction. The other advantage of a torus magnetic field is that since it is ununiform, you can have a region, the interaction region where you place your target that is field-free. The advantage is that if you want to use a polarized target, for instance, you really need to have a very good field, 1 part over 10,000. So you have to know very precisely how the uniformity of the field in that region. So you prefer to have a dedicated magnet with such characteristics, and any other magnetic field, external magnetic field, can be a kind of noise to your measurement. And the detector that keep the whole B is quite standard. We have particle identification trackers, time of flight, and electromagnetic calorimeter, and this is standard equipment for high energy physics. And the luminosity for this hole was 10 to the minus 34, 10 to the 34, sorry. But again, you have to consider that in this case, you really can cover almost the full 4 pi solid angle. So what is important is the product of the luminosity by the solid angle. So at the end, again, the number of events that you produce that you are able to collect is quite huge. Hole C is a kind of similar to hole A because it hosted 2 spectrometer with the you can consider a kind of intermediate situation between the hole B and the hole A. In this case, you have spectrometers, so traditional spectrometer, but they are very particular because you have an HMS that is high momentum spectrometer and a short orbit spectrometer with a very large 40% momentum acceptance that allows you, for instance, if you produce a single pion, you can consider the single pion electron production, you can measure all the pion. The pion goes around your virtual photon that is produced, your Q square. So you can imagine that using this spectrometer, you are able to really measure the whole 4 pi, the 2 pi angular distribution for pion emitted, having a reasonable acceptance for your detector. And then it also hosted some experiment like a G0 Q weak that were, again, let's say unconventional nuclear physics experiment, more about the parity violation to measure the weak form factors for quarks, for nucleons and quarks. The next step from the 6 GeV, this was the instrumentation at 6 GeV. Next step will be the 12 GeV. As I told you, the machine ran routinely at 6 GeV. It was originally meant to run at 4 GeV. And the design and the performance were so good, and the design was so clever that the upgrade of the machine is, quite simple. Again, just consider simple in that field. Just to give you an example, the machine has been shut down for 2 years only to double the energy. So no engineering construction has been needed because the arc, the region where the magnet, where the particle are bent, can bend up to 24, can host a magnet up to 24 GeV. So the only thing that was necessary to do was to increase, let's say, the power or the electric field for each radio frequency and add certain number of cryomodules of this radio frequency to double, mainly to double per each LINAC the energy and get at the end a machine that works at 12 GeV compared to the 10 GeV. And obviously there is also new equipment in the existing hole and a brand new hole, called the hole D, that has been added for the 12 GeV, that is mainly devoted for the spectroscopy program that Mike probably is tell you in this week very thoroughly. The 12 GeV equipment is a kind of extension, if you want, of the 6 GeV. So again, we will have the hole A with the high resolution spectrometer that will be devoted to measure specific experiment. Again, this, let's say with a small collaboration or very focused experiment. And there are also some idea for the future of the whole to build the big installation like solid Muller that are specific experiments that involve different equipment. So far, let's say that the whole will start with the SBS, that is an evolution of existing spectrometer that is better suited for the higher energy. For Hall C, again, it's a kind of extension of the previous hall that will be mainly devoted for nuclear measurements. Again, so the idea is to be able at some point to map out the nuclear-nuclear interaction in terms of quarks and gluons. And the Hall B is hosting an evolution of the previous detector, of the class detector. It's called class 12, that needs to be is again based on a toroidal field, so more or less is the same as before. The big difference is that now it has to sustain a luminosity of 10 to the 35, so 10 times more. So it means that some of the detector need to be remeasured and also need to measure particles with higher momentum, so some part of the equipment has been replaced. And this hall will be mainly devoted for the GPDs and TMDs program that you are listening in this week from Peter. Hall D has the GluX detector that I will talk more extensively in the next part. So, but again, this is mainly for photo production and hybrid Meson photo production. So this is obviously, I mean, a tiny, reduced list of the whole physics that Jefferson Lab did in more than, I guess, 15 years. I guess it's about 15 years of data taking. I'm gonna I pin down just a couple of examples. Obviously, I mean, there is no time to go in detail of these topics that require. Each of them is a long, obviously, is a long and extensive classes if you want. I just pinned down a couple of examples. So the elastic form factors, that is one of the highlights of the scientific production of the lab. That was, I mean, one important part of the previous, of the 6 GeV era, and is going to be also part of the 12 GeV era. I'm going to talk about the physics of confinement, in particular for hybrid Meson search in Hall B and Hall D. And I'm giving you just a flavor about the search for physics beyond the standard model, just to show you that even in a lab that is, let's say, traditional nuclear physics, you can also do physics that is beyond the standard model. That is really hot topics today. Okay, so let's start with the form factors. So you well know that we can consider the nucleon according to the different energy. If you want a different momentum transfer of the electron hitting the nucleon, you have a different picture of what you are looking at. At low, let's say at large distance, you see the nucleon as a whole, while if you go to smaller distance, you see the constituent quarks. But if you increase the energy, then you start to see partons, you see gluons and quarks as a single particle, let's say as a bare quarks of the in principle should be the quarks of the QCD. Degree of freedom. Now, traditionally, the way in which things are described started from, let's say, elastic scattering. That is the simplest thing that you can think about. You just scatter an electron on a nucleon, and you measure the recoiling nucleon and the scattered electron, and then you get information about the structure of the nucleon. The fact that the nucleon is a composite object, is not a single particle. This was a Nobel Prize at that time. In this way, with elastic scattering, you get information about the transverse quark distribution in the coordinate space. And so, in some sense, you are probing, if you want, the charge and the current densities. Okay. Another approach that was run again as LAC in the 80s was the deep inelastic scattering. In this case, you have information about the longitudinal quark distribution that is a kind of complementary to the elastic scattering. And now, a new technology, let's say phenomenological approach based on what they are called a generalized particle distribution, allow to put together all things together in a single view. You have a function that has limits both the elastic scattering and the DIS as a particular case of a general structure function that is called these GPDs that can be accessed running experiment with exclusive scattering in a deep inelastic regime. Obviously, again, each of these subject requires a long and extensive description, so I'm not gonna go in details. I'm just give you again flavor about the form factors that are the simplest. If you want the elastic form factor, are the simplest measurement you can imagine. And again, this give you the this is very important. You will find that this data and these results on the textbook. So it's really a fundamental property of the nucleon. The way you can express the cross-section as a function of, let's say, a point-like object multiplied by form factors. And there are two form factors, one electric and one magnetic form factor. And the way in which you experimentally can access these two information is what is so-called the Rosenbluth separation. This is what has been done traditionally. This is just to consider that the kinematic dependence of the two form factor, that is the unknown of your measurement, is different, and then changing the kinematics, you can access one or the other. The problem is that GE, that first of all is small, intrinsically smaller than GM, and the second is that is multiplied by a kinematic factor that usually suppress it. So it's very difficult to access experimentally. There is another technique that allows you to extract, or at least to measure a ratio of G over GM that actually was proposed in the 80s from some Russian people that then require the technology to be developed, because you have to measure, you have to run an experiment where you have the electron polarized, you need to have the proton polarized, and you have to measure the recoil polarization. In this case, making a ratio of the perpendicular to the parallel components of the spin, of the two components of the spin of produced proton, you get an information related to this G over GM. So it's really independent on the Rosenbluth, and it's also independent on the polarization and on all the details of the experiment. So it's from the point of view of the experimental of the experiment is really attractive, because you concentrate making a ratio, you simplify all the systematic effects that you may have. Now, this is the situation of form factors. Again, you will find this data set on textbook. This was before JLab measurements, and you see that this is a GE over GM for the proton, the same for the neutron, and then you have GM over the dipole fit, or the dipole behavior that you're expecting from the magnetic part, and the same for the neutron. And as you can see, the common, I mean, just looking at this plot, you can say that, okay, the electric and magnetic are related. They are almost following a flat line. And that, so you can argue from here that what is causing the electric form factor and what is causing the magnetism, so in some sense the charge and the current distribution within the nucleon should be strongly related, because there is a proportionality of them. After that, Jefferson Lab extended the measurements at large Q squared, so we are picking up the components of small distances. You see that using a different experimental technique, you see clearly that the G is not at all proportional to GM, is different. So it's probing that there is a difference in G and GM. And this was, and obviously there was also, this extension of GE for neutron that was really, just measuring a very tiny part. So this was one of the let's say, more important results obtained by the lab that again show you that the magnetism and the charge density within the proton are a little bit different, so needs to be carefully considered. Obviously, I mean, people interpret the data having the new data. The point is that you really need to consider all the ingredients that usually were considered as a secondary effect or a second order effect needs to be included, like for instance the correct treatment of the orbital angular momentum or the pion cloud. You can imagine that you have a pion cloud. Obviously this distorts your naive expectation that the charge and spin are produced by the same cause. And now obviously it's the question is why people in the past there is this big discrepancy between the Rosenbluth and the measurements with polarization. We believe this is based on the article just produced from again from JLab last year. We believe that we found why measurements of the Rosenbluth can produce fake results. If you look at the kind of diagrams that you have to consider when you study the electron scattering, you have obviously the simple approximation. This is the Born approximation, where you have a single photon exchanged. You may have correction due to the radiation of photon before or after the interaction of the electron with the nucleon. And you have vertex correction, like reported here, but you can also have the case where you have two photon exchanged. So this second that was usually neglected in the past to describe the electron scattering. And if you consider in particular these two photon exchange, you get a new pieces that together with the cross section, together with the standard formula that you have for the dependence on G and Gm, you have another part that multiply. And there is a way to access, I mean, to have a sensitivity to that specific part. If you run, if you take the ratio between scattering of positron and electron, you get something. Just making the ratio of the two, you have simplification of the most part of the formula, and you have 1 plus something that is proportional to these two photon exchange contribution. And this is exactly what we were able to do, running positron in the hole, producing positron from a photon beam that produce E plus E minus pairs, and recollecting E plus E minus and using these E plus E minus pairs to run a positron and an electron experiment at the same time. So we really, again, minimize the systematic effect due to comparison of experiment running in completely different conditions, positron and electron beam. And the final results was that if you correct the unpolarized measurements that was performed also at JLab, confirming what people observed in the past, mainly from SLAC, if you correct the unpolarized results by this new factor that you have to include, you get points that are perfectly aligned on what you measure with the polarized experiment. So again, this probably there are still, I mean, some debate if also the radiative correction can be responsible for this effect, but I think that this is quite a strong evidence that the two photon exchange may play and are playing a role in the business. Same thing for the nucleon structure, that again is quite interesting, because the measurements, the extension of the measurements that was able after from Jefferson lab show you that even if the charge distribution in the neutron as a whole, again, just looking at the nucleon from far away, you see a single uncharged particle. But then if you go in details and you try to map out the charge distribution that is possible, increasing the Q squared that correspond to smaller size, you really see that there is a compensation of a charge distribution that is absolutely, I mean, has to be correctly described to explain this behavior in Q squared. So again, this is just to show you that some of the results that were obtained by the measurements. So the bottom line is that everything is understood as far as you are considering correctly the relativity in the right way, and you also include the pion cloud. That is also important not only for the elastic form factor but also for transition form factor. It's one of the main ingredients that you need to have to describe correctly the behavior of transition from the nucleon, for instance, to excited states like the delta or like other resonances. Okay, so let's see, this is the form factor plans for 12 GeV. So this is the situation as per today. And this is the situation that we are expecting you have the blue points are the measurements, what Jefferson Lab is going to add in the next few years. You see that we will have an enhancement, I mean, a climatic coverage that extend sizably the GE of the proton, but in particular there will also be a detail and with tiny error bars measurement of GM, and also for the neutron there will be an important point put at large Q squared that again is going to constrain the different models that you have that now are only constrained in the region at low Q squared. So will be very important to measure. So this is the plan for already approved experiment with runtime already allocated. The second example that, again, is more projected for the future, we also run some spectroscopy, hadron spectroscopy at 6 GeV, is about the gluon interaction in QCD, and this is the subject that Mike is going to cover in this day. So I'm just give you a feeling from an experimental point of view. I don't want to, obviously, to jump in Mike's field that is able to describe things and explain things much better than me. Just want you to take a hint. It is important, in my opinion, very important point, that is if you think about the nucleon, that is 1 GeV, and you think about the quarks, the light quarks masses together, you get only few % of the whole energy. So it's clear that if we want to understand our world, we need to understand light quark, because the matter is made by light quark, it's not made by charm, bottom or top quarks. So we really need to understand it. And since the bare mass that is due, if you want, to the Higgs mechanism, to low energy, that was describing and taking producing the mass for high mass quarks is only, again, a tiny fraction for the light quark. So it's clear that we need to understand the confinement, since the mass of the nucleon, and so the mass of the universe, if you want, is related to the non-perturbative regime of QCD, where you have gluons that act as a binding energy that makes the gross feature of the mass of the particle. So I think that this is the simple message that explains why I think spectroscopy is so important to understand our world. In particular, the Meson spectrum, the tools that we have in our hands is a very simple constituent quark model, and if you want, you can ask yourself, how is it possible that such a simple model that predicts the existence simply of a quark and anti-quark can reproduce more or less the most part of the phenomenology that we observed, so the zoo of particles that we observed. You can combine a quark and anti-quark, have quantum numbers carried by the quark and the anti-quark put together, and you can find states with well-defined spin, parity, and charge conjugation. And obviously, you find that not all possible combination of these quantum numbers are possible. There are a certain, if you assume that you have a quark and anti-quark as a starting point, you can only have some combination of quantum numbers. Then you add the S3 flavor symmetry, for instance, and you get nonets. That is exactly what you observed. It is more or less states that have the same mass, with a little difference due to the violation of SU3 that we know, because the strange quark has a mass different from the up and down. So clearly you are expecting to have a kind of violation of SU3, at least due to the different quark masses. And then it's quite unbelievable that such a very simple model can reproduce the most part of things. But since it is simple, it doesn't reproduce actually everything, and there are other possible configurations that are allowed, or at least are not prohibited by QCD, like having, for instance, four quarks together, or having glue balls, where you only have gluons in some sense, or hybrid mesons, where you have the quark and anti-quark, and then you have the gluons that actively participate to the dynamics of your meson. Okay, so you can imagine that you have this, again, these other particles that were not where, let's say, there were some hints, some suggestions about their existence, but it was never clearly shown that there are other configurations other than the 3 quarks or the QQ-bar configurations. And obviously, this is strongly connected with the gluon field, because again, both the glue balls that are made only by gluons or hybrids needs to have participation, explicit participation of gluons to the dynamic of your meson. So it's clear that this will be very important. I mean, detecting this particle, knowing their masses will be very important to understanding, to have information about the forces that bind the quarks, that means the QCD field. So experimentally, how we can try to disentangle and to get information about hybrid mesons. It is, again, principle is quite simple. You have, as I told you before, you have some combinations that are not allowed by simple QQ-bar picture, but in principle, if you can add the quantum numbers of your gluons, or you put some extra dynamics, you have a different combination. So the idea is to pin down, to measure quantum number of states that has these quantum numbers not compatible with QQ-bar. And this will be the proof. Actually, it will be part of the one, at least the minimum proof of the existence of hybrid mesons and the configuration in parallel of the QQ-bar. At the same time, this is from the experimental point of view. So we are looking for states with quantum numbers that are not compatible with the QQ-bar configuration. On the other hand, in the last few years, there was a big, I think, big progresses in lattice calculation. You know, it is a way to solve the QCD Lagrangian with the computer. And even if there are still a lot of problems, or if you want approximation in the procedures, for instance, the pion mass, or if you want the quark masses, is not the one that you should use, and there is a trend to reduce and to make the world that lattice QCD is describing as close as possible to the real world. And the important thing is that now the machinery that is in place, is producing results, and show not only the standard mesons as more or less as you are expecting to see, because at least the machinery needs to reproduce what is well known, like the standard meson. They also predict some exotic states, and they also predict, if you want, the relative mass of these exotic states, that even if you can consider the numbers here precise in terms of absolute value, give you, let's say, the strength, the existence of these states, and the relative strengths of these states respect to the known one should remain more or less the same. Kind of hierarchy that is conserved, even if the absolute value will change because the pion mass is different from the one that corresponds to the real world. And the other big advantage of the new machinery that people, in particular at Jefferson Lab, there is a big effort, a theoretical effort on that. They were also able to project the states on operators with the quantum numbers, with the finite quantum numbers, so they can also extract the composition of these different states in terms of quantum numbers. And so identify, if you want, the exotic components or the traditional components for the other mesons. And what they found is something that, again, you may expect just naively. That means that these gluonic excitation are mixing with the standard quarks picture that we have. So it's obviously very difficult to completely disentangle. There are states that present stronger components of glue respect to others, and this is where experimentalists need to focus their search. Same thing in terms, for instance, of isospin composition of mesons that, again, show that they are able to have, let's say, at least a guess about the strange or the UND components that allows, again, to look for specific decay and helping so the experimental search. The other important thing is that the energy of the states that we are expecting to have, like a hybrid and exotic meson, lies in the range between 1.4 to 3 GeV. And this is exactly the range that you can reach with 10 GeV. About 10 GeV photon beam. So this is the reason why the upgrade of Jefferson Lab was matched on 12 GeV mainly, because at that time the whole D and the hybrid meson spectroscopy was the flagship, if you want, to motivate the whole upgrade. To measure these new mesons, you need to have detectors. I already told you that there are 2 of them, one in hole B and one in hole D, that are hermetic, so allows you to measure the full final states, or many different final states. And then you have to run partial wave analysis that allows you to disentangle the quantum numbers. So you will see in details in Mike's lectures how you can do that. It's complicated, but can be done, probably. Photo production. One important thing is that why we are using photo production to produce hybrid mesons. Again, this is traditionally the spectroscopy has been run mainly with pion and kaon beams in the past. Again, if you think a little bit, it's quite easy to understand. The photons carry spin 1, so it means that you can produce hybrids that doesn't require a spin flip to be exotic. So you can excite, if you want, that is exotic quantum numbers easily with photons with already having a unity of spin than using a spinless particle like a pion. And there is another reason that is based on prediction, based on phenomenological model. The rate, if you want, the probability to produce these hybrid mesons is not much different from what you are expecting from the standard meson. For instance, here is the A2 that is a standard meson, or the P1 that is an exotic meson, and you see that the cross section more or less in the same range. I mean, it's not 100 times smaller than the other. It's maybe a few times smaller. This is what we are expecting. That doesn't mean that this is really what we are going to find. Now, if you start with 10, 12 GeV electron beam and you want to produce a photon beam of corresponding energy, there are only a few options. One is the Bremsstrahlung. The other is the low Q square electroproduction. These are the 2 techniques that were used by the 2 holes, hole D and hole B. In particular, hole B is going to using the coherent Bremsstrahlung on a crystal. So you hit a diamond crystal with an electron beam, you produce a photon by simply Bremsstrahlung, but the photons that are produced are polarized, are linearly polarized, because they keep the structure of the lattice, of the diamond lattice. So you produce photons, and then you collimate, and you get a peak, starting from the 12 GeV, you get a peak at around 9 GeV with high linearly polarized photons. And this is the standard technique that we already used in the hole B for many years during this 6 GeV era. Hole D has been built from scratch. Detectors has been assembled again from scratch. And now the commission is in progress, so I think it's a big success of the lab to keep the process. For the whole B, using a different technique that is the electroproduction, so you can imagine that we run a real electroproduction experiment. The only point is that if you get the electron at a very small angle, let's say a few degrees, you get the Q square of the exchanged photons that is very small, let's say 10 to the minus 2. So you can consider a 10 to the minus 2 in Q square virtual photon almost the same, at least from the point of view of the production, as a real photon. This is the assumption that we are doing, that seems to be reasonable. And so this is the technique that will be used. And if you make some calculation, you found that the rate that you can produce, the flux, if you want, of the equivalent flux of virtual photon is very similar to what you can get with the Bremsstrahlung. So we should have 2 different experiments, one in hole B, one in hole D, that measure photon with different techniques, Bremsstrahlung and low Q square electroproduction. In particular, for low Q square electroproduction, you need to measure electron scattered at small angles. So a piece of equipment that is necessary to have is a calorimeter, covering from a few, let's say 2-3 degrees up to 5 degrees. That was not originally included in the base equipment for the hole, and this is what we are involved in. Now, this is only a tiny part. I mean, measuring your states, your final states, is only a tiny part of the whole business, because the big part, the big chunk and difficult part, in my opinion, is the theoretical interpretation of the data that you get. And this is based, as you probably learn, if you don't know already, based on partial wave analysis. So the idea is that you can infer you have a sequence of decays of particles that use your final states that you measure, and then you can come back to the original particles that was produced by at the vertex, and then you can infer from just measuring the decay distribution of these particles, you can infer the quantum numbers of intermediate states and go back to the original particle. This is, I mean, the same idea that should work. Unfortunately, reality is much more complicated. First of all, this simple assumption is based on the fact that you always have a kind of two particles production is based it's a kind of isobar model, so you're expecting to have only two body in two body, while in reality you may have effect due to the three body interacting all together. In this case, you are totally ignoring that there is a baryon. This part is totally ignored, while in reality, again, unless you go in a very pure kinematics, you have to in some way describe the presence of the proton. That, okay, you're interested to the meson part, but the proton, I mean, the baryon part is still there. So in principle, what we should have is really to have a full understanding of the amplitude that describe the process as a whole. So with the final state, with all particle in the final state, and this is the Graal, if you want, that we're expecting to have. It is not clear if we'll have or have. Just to give you an example of partial wave analysis, that is the 3-pion production. That was one of the candidates, the pi 1/1600. It was one of the candidates to be exotic, because if you look at a decay of this resonance in a rho pi channel, then the rho decay in 2 pions, the rho pi in the p wave correspond to a quantum number of the original system 1 minus plus. That is one of the forbidden states that we discussed before, okay? So, I mean, again, quite simple. You have to measure a rho or a pions and see that they are in p waves, they resonate, you find the resonance, and that's it. Unfortunately, this is the results, for instance, from EA52 experiment that ran in, I guess, 89, 90, something like that. And I mean, it was very confused that they produced a paper claiming the existence of these hybrids, and then a reanalysis of high statistics data sample showed that, I mean, moved from this peak that was associated with the pi 1/1600 to this. I mean, almost background shape. Then we repeat this experiment with the limited statistics of class with the 6 GeV, and again, we were able to see the A2, so some mesons that you were expected to see, while we were not able to see the pi 1/1600 in our first run. Then we ran high statistic runs, again at 6 GeV. This is the spectrum, so you see the statistics, how it was improved. This is the 6 GeV data. And again, we were able to map out very well the existing, or I mean, what you are expecting, the mesons that we know should be there, while for the rho pi in P wave, again, there is no hint. So, I mean, whatever, obviously the statistics can be higher, maybe the pi 1, even if this is the lowest state, even predicted by lattice QCD, is not there. Maybe we cannot be excited by photo production. But I mean, I think that the bottom line here is that experimenting photo production already showed the capability of doing spectroscopy. That was not so, I mean, so obvious up to, let's say, 5 or 10 years ago. There are still some people that believe that only hadron probes can produce copiously a lot of particles, or only E plus E minus machine can do spectroscopy. Why? I mean, we proved that we were able at least to measure existing mesons that you know that should be there. So here are, for instance, an expectation for GLU X whole D and meson X whole B experiment, and this kind of experiment will not only be studied at Jefferson Lab. Obviously, for the future, we are waiting for Panda GSI, and now we have experiment running at LHCb. Bestri and Chloe did a lot of spectroscopy on different states. In particular, Bestri is doing a lot of spectroscopy also in the light quark sector. So it is a kind of a general effort that we are, just started with the 6 GeV and will be finalized with the 12 GeV. Now, let me go to the very last argument, that is the last topics, that is the dark forces and like dark matter search. This is quite different from, let's say, the standard nuclear physics. And the question is how to look for new physics. You notice, again, a topic that everybody would like to see something new other than the Higgs boson. And other than having a confirmation of the standard model, you should be more excited to see something that doesn't fit in the standard model. Now, the common belief in the past was that you can excite. The new physics is high energy, so it is called the energy frontier. High energy with coupling that is in the range of standard model coupling, so the weak coupling constant. But what about if the new physics is not a high energy, but is a low energy, let's say a few GeV range? With the difference with the other scenario is that now you are considering it is physics at low masses, but very weakly coupled to the standard model. With coupling constant that can be millions of times smaller than what we have for the standard forces. So this is a kind of a new frontier that is called the intensity frontier, where machine that has intense, in particular electron beam that are quite clean from the point of view of the probe, even if the energy is moderate, you can really explore very thoroughly this kinematic domain. In particular, we all know that there are 4 forces. Now, I'm just describing a couple of scenarios that motivated this search, that may be just inventions of theoreticians, but maybe also the reality, why not? So at least it's worth to be investigated. One point is clear, that the dark matter, at least cosmologic dark matter, cosmic dark matter exists, because you have a lot of proof on that. Now, the question is this dark matter, as for the standard model, can be related to particles, have new particles that carries that are responsible for the dark matter? You have new forces that bind together the dark matter, for instance. And one possibility, one scenario again, that has been explored, is that you have a new U boson, so it's a kind of extension of the electromagnetic interaction that can be considered as the simplest, if you want, the simplest extension of the standard model Lagrangian, where you have an extra U1, so very similar to a hypercharge that describes the electromagnetic interaction. So you have another particles that is this heavy photon. In principle, the photon, these new particles, has mass. And the way in which you connect it is a hidden sector, that is where the dark matter lives, very high energy. You will never get it, you'll never found it directly. And the standard model is that via these messengers, they call it the messengers because they mediate the interaction. Obviously, it is a construction, it's invention, maybe it's wrong, I don't know. But just copying what we are used to see in particle physics in standard model, you have, for instance, the effect of heavy quarks, even in the low energy regime, by loops. You have loops where particles, very high mass particle participate, and you have a contribution of this correction that affect your physics at low energy. This is exactly the same idea. You can think that these high energy mass dark matter particles will never, with energy, let's say EV or even higher, will never be produced in an accelerator or will never be detected directly. But the effect of them can be seen as a tiny correction to what we know about the physics that we describe within the standard model. So this is every time, in some sense, that you have a photon, you have this possibility of kinematic coupling with this heavy photon. And obviously, a kind of coherence of all the picture is that you have the dark matter with the new forces that is responsible to let the dark matter interact, and also responsible to let the dark matter interact with the standard model. There are different scenarios. I'm not going in details. I just want to tell you that there is this idea of heavy WIMPs, so heavy weakly interacting massive particle, as I showed you before, but there is also the possibility to accommodate light WIMPs, so the dark matter particles as mass in the GeV range. You know that the direct search of dark masses is limited as a minimum mass of dark matter around 10 or few GeV, simply because the experimental technique that is used requires scattering on nuclei, and nuclei are massive, so you can't go lower because there is no transfer energy, so you don't see the signal, even if it could be. So the idea is that with the accelerator, you can really test, in particular with the high-intensity electron beam, you can probe all this region that is totally excluded by a direct search in the standard, let's say, dark matter experiments. There are some astrophysical motivations that motivate search for bosons at low masses. For instance, if you look at the excess of positron measured by AMS and Pamela experiments, that show an increase of a high-energy positron that is not easily explainable within the cosmic models that we have. At the same time, the ratio of antiproton goes like expected, so you may imagine some mechanism that produces positron but doesn't produce antiproton. That may be compatible, may indicate that the particles can only decay in E plus E minus and can decay in proton-antiproton. So it means that probably this particle needs to have a mass lower than two times the mass of a proton. These are really indirect. There is not a probe of anything, if you want. This is just an indication that may be consistent with this picture. There is another effect that you are expecting if you assume that you have new particles around, like, for instance, modification of the standard electromagnetic current. In particular, we know that the G-2 of muon shows some discrepancy respect to what you are expecting. After that, all the corrections are applied. We know that there are corrections due to the electroweak and the hadronic part for the simple description of the spin of the muon. So if you apply all this correction at the end, you find the discrepancy. So again, maybe related to some physics. Again, if you just think that there is another particle, another possible force acting on the muon, obviously you have to consider this correction, and including this correction, calculating this correction, you find that it goes in the right direction. This may be responsible for that. So from 2008, let's say, started a search for, in particular, for this new boson, the A prime, and all labs in the world participated. Not only Jefferson Lab, with this specific fixed target experiment. There were attempts in Babar, for instance, in E plus E minus, but also at LHC with hadron collision, and also with the meson decays. That is another way to probe discrepancy between what you are expecting from the standard model and the possible contribution from physics beyond the standard model. And this is the situation in 2008, when all this search, had this boost. This parameter space represents the mass of this new boson, and this is the coupling. As I told you, it should be small, because if not, we probably have already seen the effect. So it should be small, so we are in a range where you really need to have a lot of charge, a lot of particles to the system to check something. And the Jefferson Lab had at least 3 experiments running on that specific search. This one of the 3 is HPS, is called the heavy photon search. The idea is very simple. You have the electron producing by Brennstrahlung on a nucleus photons, and some of these photons can fluctuate in a new A prime, and the A prime decay in E plus E minus, and you measure E plus E minus. What you are expecting is let's say, a smooth background due to the standard radiative and Eichler processes, where you just produce E plus E minus by the standard QED processes. And you are expecting to see, if you produce here a particle in intermediate states, you're expecting to see here a bump. So it's, again, very simple. The experimental technique and the experiment is quite simple. You just measure You just measure E plus E minus and check for a bump. There is another little trick that if you not only look at this bump and integrating that you measure, but also detecting a possible detached vertex from the original point, from the target point, you should be able to see that lives for a while. If they live for a while, it means that their coupling is small, coupling to the standard model. So you are really probing a region of coupling that is very, very small. And this is the kind of technique that is going to cover in the next. HPS is running these days. Is running in April, in March, and from March to May this year. So we are getting data very soon. We will cover that part that is not covered. This is left open by the other experiment. But as I told you, Babar, Chloe, Hades, you have experimented SLAC, you have experimented MINDS, cover most part of the phase space. And new experiment, the Jefferson Lab, APX, HPS, and dark light here will almost close all this region in the case that no signal will be observed, obviously, okay? Excluding this scenario. So I think this is, again, very important to highlight. Obviously, there is another option that you may want to include if your particles, if your A prime can decay plus E minus, but can, if the dark matter is light enough, it can also decay in light matter. In dark matter, so probably it's even more natural to think that it decays in dark matter. So in this case, together with the visible decay of the A prime, you may also consider a process where you produce dark, this A prime, the decay in a Chi-Chi bar, in the pairs of particle and antiparticle of dark matter. Okay, fermions or even scalars, it's more or less the same approach. In this case, so you want to run an experiment a little bit different, where you have an intense electron beam that hit a dump. So at the end of your beam dump, you have dirt, so dust that simply shield the standard model particle to reach the detector, other than probably neutrinos that are the only one that can survive to an heavy shield, but they are so tiny produced that should not be the case. And then the idea is that you may see a signal within the detector or a scattering of this particle on a nucleus or on a nucleon or to scattering over an electron. Depending on that, you will see different signatures. There are possibility to measure different things. So this is another kind of experiment that is going to be, has been proposed at Jefferson Lab and is going to run in the future. And again, I don't want to go in detail. The bottom line of this slide is that having a campaign that will investigate both the visible and invisible decay, you can rule out or you can confirm this picture of light-dark matter. That in any case is interesting. Is interesting because if you rule out, you can really, you need to look for dark matter in a different range. If you see something, obviously you will get the Nobel Prize, but this is probably not the case. So anyway, it's interesting for the future of the lab. So my conclusions. I hope I give you just a flavor about it. This is only, a very tiny part of the program of the Jefferson Lab. For factors, there is a long list of other important searches that Jefferson Lab did, some exploratory measurements that will be done in a better way with a better, more suitable kinematics at 12 GeV. I just gave you, a very brief and couple of examples of that. The point is that we are trying to understand how hadrons are constructed from degree of freedom of QCD. That is, I think it's per se is very interesting because, the world is made by hadrons mainly, dark matter and hadrons. Okay? But at least the baryonic part, the hadronic part, needs to be understood in terms of QCD degree of freedom. And we not yet have this kind of understanding. We don't even understand exactly the spin of the nucleon. We have problems to understand the very simple things. So I think that this program that is going to run for the next 10 years from now, as soon as the Jefferson Lab is going to take in data 12 GeV, will clarify some of these issues, hopefully. And then together with this understanding of, let's say, the traditional and standard nuclear physics, Jefferson Lab is also pursuing a different path that is showing that you can do physics beyond the standard model, even such a low energy machine that, again, it was a kind of I don't know how you can say bestemia in English, but something very bad that people up to, if you just up to a few years ago, you talk about the possibility of using low energy machine to do physics beyond the standard model, people at CERN, they will immediately say that it was absolutely impossible. While, I mean, we demonstrated that you can at least concentrate and focus on some scenarios where the low energy machine can do better than high energy Hadron Colliders. And just want to conclude showing the first interaction in the whole D that was taken, you see, in the very, at the end of last year. This is a pion, this is a pi 0 with the two gammas building together a pi 0. For the first time was measured in the brand new detector of whole D. And this is the spot of the beam hitting the whole B. So, I mean, we are doing, I mean, a lot of progress, and hopefully next year we are starting with physics. Thank you.
So, any questions for Marco?
So the standard way that people use so far is based on what I told you is called the isobar model. So the idea is that you produce particles that are stable states that decays, okay? And you have a sequence of decays. Now, it's clearly not the case because, I mean, resonances lives only for a tiny time, and therefore is not completely obvious from the theoretical point of view implement a state that is not stable with the isobar model. This is the first problem. So you have to parameterize in some way the fact that these particles lives, so they have a width, if you want, in mass. So they're not a fixed mass, they have a width. First of all. Second point is that this sequence of two-body decays completely ignore the fact that you may have three-body effects. You may have particles that interact not only at level of 2 in 2, but since you are producing a state with 3 particles in the final state, you may have these new particles that, I mean, all particles in the dynamics. Obviously, they are tiny effects, and we know that the isobar model is perfectly fine. This idea, this simplification, these hypotheses are perfectly fine if you look for, let's say, signals that are at a significant fraction of the states that you produce. But as soon as you are talking about tiny contribution, and for sure, hybrids or exotics or glue balls will be a tiny contribution to the cross-section. If not, again, they will already shows up in the spectra, so it's clear that they are small. Since they are small, the problem is that you have to control your theory at the same level of the signal. So if you are talking about a signal of 1%, it means that you have to understand everything else at the level of better than 1%, okay? This is the problem. Obviously, if exotics will show up with a cross-section that are 10% of the full cross-section, no problem. We'll see them, we'll immediately find them, no problem. But if, as probably we are all, I mean, all people working in spectroscopy believe that the cross-section will be tiny, I mean, the strength, the probability to produce this state is small, then you really need to have control all the other effects at that percent. For instance, again, I already mentioned that, but totally ignoring the baryonic part is obviously wrong. How much is wrong? How much can we ignore that you are producing a meson on a proton? How much is this approximation good or bad? For sure, I mean, it's not so bad because again, the gross feature of the cross-section is expressed in this way. But are we sure that the remaining effect of this nucleon that participate to the full dynamics, because I mean it's part of the dynamics, is entering some way also in your final meson production? So in that sense, I think that the only response, the only correct way is to really try to consider the final state in its complexity, in everything. You have to have an amplitude, because obviously you describe a process, so you need an amplitude. The amplitude needs to depend on all variables, all particles that you have. This is the main point, in my opinion. First. Second, the amplitude needs to satisfy all the theoretical requirements. You know that, for instance, Bright-Wigner is not satisfying anything. 99% of analyses are based on Bright-Wigner parametrization of resonances. The sigma, the two pions resonating in the S wave is a very simple. I mean, we are talking about two pions that produce a kind of resonance at few hundred MeV. So it's very simple, low energy. I mean, nothing complicated involved in that. Yeah, you know that these particles that we believe to have well understood now is not cannot be described as a Bright-Wigner. It's not a bump. You really need, it depends on how the resonant is, and you have to apply all the correct machinery. Applying the correct machinery doesn't ensure that you get the hybrids, but if you are not applying the correct machinery, it's sure that you can get the hybrids. This is my point. So I think that more than an experimental effort, because I can show you results from COMPASS, for instance, that use the pions, few hundred GeV pions over a nuclear and nucleon target, and they have spectra that are wonderful. I mean, you see perfectly, I mean, huge statistics. They can be in many kinematic variables. The problem is, again, that it's not the quality of the data. Quality of the data will be very good in the future. I mean, with the new experiment, PANDA, COMPASS, BESS, Jefferson Lab. The problem is that you need to have a framework, an analysis framework that is sound, that is correct from the theoretical point of view. Needs to implement the unitarity, all the constraints that you have to have when you analyze these things. And that's incredible how, for instance, we tried, I mean, Mike and Adam found that the old Veneziano model that was used in the 70s to describe the omega decay, so again, something that now after it was in the 70s and now it's 40 years later, we hope to have completely understood, was applied to the J-psi decay in 3 pions, producing a very nice results. And this is the other trick, I think, that you really need to have a framework that reduces the degree of freedom that you can put in. You cannot put whatever you want in your description. You need to stick with the well-defined set of states, if you want, because if not, I mean, you can put or not put whatever you like, and you put in. Exactly. This is also the reason why the spectroscopy is not light quark spectroscopy is not very attractive for theoreticians, because it's complicated. It's really very, very difficult. It's much difficult than the charmonium.
But also let's say in the heavy sector, you see that even if you place
Absolutely. Absolutely. Yes. Absolutely. Yeah. For instance, XYZ now, that famous states found by Babar and then by Bess and Bell, confirmed by many different, they see bumps, but are you sure that bumps correspond to resonances?
From my experience in my field, it's just that experimentalists want to analyze their own way. They know how to apply it, and there is no. This is in my field. I don't know whether it applies to me.
I think it applied too in our field.
They refuse basic quantum mechanics.
It's a different, sensibility. No, but it's true. Exactly what happens also in our field. I think that due to the big effort, the Jefferson Lab, setting up a JPAC, for instance, I mean, this analysis center that Mike and Adam built, and also having this worldwide effort, because it's obviously not being, I mean, exotics will not be found by GLUEX, by CLASS, by COMPASS, but you really need to analyze the data, all the data from different probes, all together in a consistent framework. This is the only way. It's a long way. Maybe we can decide that it's too long and doesn't work. I mean, it's not an easy business for sure. It's a very complicated business. But I think that our community now, low energy physics, start to yes, I think so. To realize, yes. And this was, I mean, not easy. There was a lot of schools, a lot of, workshop, dedicated focus workshop on that. And you find people that describe things done, for instance, at BESS, so high energy side, that still use tools that we all know are wrong, are absolutely wrong, that may be good for, for big signals, but they are not good a priori. They are wrong. So